Number 1. April has $200 to invest in a bank. Walden Savings Bank is offering her an annual interest rate of 6.5% compounding annually. KeyBank is offering her an annual rate of 5% compounding monthly, assuming she does not make any deposits or withdrawals. So she's not adding any money, she's not taking out any money, she's just letting it sit there and gain interest. Write two functions for W of t and K of t, the amount of money in the account at Walden Savings Bank and KeyBank after t years respectively. So first let's deal with Walden. Walden Savings Bank is offering her an annual interest rate of 6.5% compounding annually. So W of t equals, well, we're starting with 200, and we're increasing it by 6.5% compounding annually. So I don't need to do any conversions here. It's just 1 plus, make that percent a decimal. Please go to your calculator. 6.5 divided by 100. I don't want it to be a percent anymore. 0.065 plus 0.065 raised to the t power. That's a function for Walden. KeyBank is a little bit more work. KeyBank's a little bit more work because we're compounding monthly. So K of t equals, I'm still starting with the $200, 1 plus, because I'm growing my money here. That 1 represents the initial $200. It's 5%, which is 0.05. But that happens 12 months. It's compounding monthly. And I can't just raise it to the t, because t is years. 12t, because if t is years, 12t is how many months? So if I put a 1 in there, that's really 12 months. So we have to be careful when we're compounding monthly. The only change is we divide the interest rate by how many times it happens and raise it to how many times it happens. So there are two functions for K of t and W of t. April plans to leave her money in the bank for 4 years. So t equals 4. Because t is years, t equals 4. Which bank should April invest her money in? Justify your answer. So we need to find W of 4. 200 times 1 plus 0.065 to the 4. And now this is just going into our calculator and typing that in. So we want to do 200 times 1 plus 0.0, too many decimals, 1.065 raised to the 4. This is the first function, I believe Walden. Yes, W, Walden. So 257. That's how many dollars. Remember, since money goes to 2 decimal places, look at the third to see how we round. We chop it off because it's less than 5. So 0.29. We have 29 cents. That's how much Walden will have after 4 years with that interest rate. KeyBank, we need to plug in a 4. 200 times 1 plus 0.05 over 12 raised to the... Sometimes it might be easy to do this in your head. 12 times 4. 12 times 4 is 48. So maybe you just type in a 48 there. 200 times 1 plus... Now, if you have a fraction template, now's a really great time to use that. 0.05 out of 12, just to keep things organized. Raised to the... If you have a TI-83, make sure this is in parentheses. You can type in 12 times 4 or just type in 48. Doesn't matter. So at KeyBank, she has 244, 2 places, look at the third, round up. So 17 rounds up to 18. 244, 18. 244, 18. So which bank should April invest her money in? April should invest her money in Walden Savings Bank. Walden Savings Bank. Number 2, a bank has a nominal interest rate of 1.5%. So nominal interest rate is the yearly rate, and every year the nominal rate is 1.5%, and it compounds interest at the end of each 6-month period. So we're not compounding annually. Every 6 months I get that interest. If an initial amount of $1,000 was invested, how much money would be in the account after 3.5 years? Okay, so let's write a function. There's my initial amount. I'm growing it by 1.5%. The minute you see 1.5%, make it a decimal. 1.5 divided by 100. Make that percent a decimal. So 0.015. But it's compounding every 6 months. So how many times does that happen a year? Every 6 months happens twice, so n equals 2. 6 months, that happens twice. 12 months monthly happens 12 times a year. 6 months happens 2 times a year. So I'm going to divide that by 2 and raise it to the 2t. Because that 1.5% is an annual interest rate, but I'm compounding every 6 months. So after 3.5 years, let's call that f of t, we want to find f of 3.5. We want to find the future value of this account 3.5 years from now. For 2 times 3.5 is 7. 2 times 3.5 is 7, so I just go and type this in. 1,000 times 1 plus. I'm going to use a fraction template. Doesn't matter if you do or don't. Just hit division otherwise. Divided by 2. Raised to the, if you don't have a TI-83, you might as well just type in 7. Or you could just type in 2 times 3.5. How much money will she have? Or we don't know who it is, who's investing this money. How much money will there be in the account? 1,053 round up to 70. So 1,053 round up to 70. That's how much money will be in there after 3.5 years. Number 3, an investment of $500 is made at a 2.8% annual interest rate compounded monthly. That's important that we're compounding monthly. So n equals 12 because it happens 12 times a year. Because my 2.8% interest rate is an annual interest rate, so we need to do some kind of conversion there. Find the amount of money in the account after 6.25 years. Okay, so this is a standard question. We have $500 as our principal times 1 plus the decimal. The rate as a decimal, so 0.028. But that's an annual rate. It happens 12 times. Raised to the 12t. Raised to the 12t. That's our future value function. That's the value of this amount of money after t years. So after 6.5 years, I'm going to find f of 6.25, which equals 500 times 1 plus 0.028 over 12 to the 12 times 6.25. And now I just need to type this in. Let me clear that all out. 500 times 1 plus 0.028 over 12 raised to the 12 times 6.25. So after 6.25 years, we're going to have $595.50. So I'm going to round to 2 places. This is going to equal 595.50. While the nominal annual percent rate of change is 2.8%. That's the nominal annual interest rate. Nominal means in name only. When we're compounding monthly, we're not getting 2.8%. We're actually getting more than that. And properties of exponents can be used to reveal the actual or the effective annual percent rate of change. Determine the effective rate for this investment. So let's go up here. Let's go back to our future value function. First of all, let's figure out what's 1 plus 0.028. 1 plus 0.028 out of 12. I have an extra 0 there, and an extra 2. Too many extra numbers. Delete. Enter. So that's what's inside the parentheses there. It's really 1.002333333 raised to the 12t. That number is what's inside the parentheses here. So it's really that number there raised to the 12t. Well, we can use a power to a power rule, and well, let's raise that to the 12th power. Let's do 500 times 1 plus 0.028 over 12 raised to the 12th power And then we'll raise that to the t power. Let's figure out what this inside number is by doing that 12th power first. And that'll tell us the annual rate. So let's raise that number to the 12th power. And this will tell us the effective rate. This will tell us what rate the money is actually growing at. So let me just drag that on here so I don't need to keep flipping back and forth. The annual rate is, I want to stop drawing lines on that. The annual rate is, well, there's it as a decimal, 2.836 and so on. So it's actually bigger than what it's, the nominal rate is. It's more than 2.8%. It's 2.836%. So now I can shrink this, make this smaller. So after raising it to the 12th power, there's our rate. Well, that 1 is just representing the 1 plus. So multiply that 100, 2.836 about percent. So compounding monthly is actually giving us a larger rate than if we were just to compound annually at 2.8%. We're actually getting more money, which is why this is actually the effective rate. We're getting more money. So we can just raise it to the 12th power. We can use that power to a power rule to get the annual rate. Number 4, a checking account has a 2% fee. We do not like fees. Fees mean you're losing money. If a checking account is not used during a year, an account of $10,000 is left inactive for 4 years. So I didn't touch this account for 4 years, but they're charging me that fee. Change our future value model so it represents exponential decay. So maybe if you think back to Algebra 1, you'll remember that I can do 10,000 times 1, not 1 plus. If I want decay, I'm going to do 1 minus 0.02 raised to the t power. So I'm going to do 1 minus the rate as a decimal. So f of 4 years it was left inactive is going to be 10,000, not 1,000. 10,000 times 1 minus 0.02 is 0.98 to the 4. That'll tell me how much money is left after 4 years. Because I'm losing money, it makes sense that b is less than 1. It makes sense that that number is smaller than 1. So 10,000 times 0.2 sets of parentheses, I don't need them, times 0.98 raised to the 4. And, wow, it's a lot of money gone. We'll be left with only $9,223.68. So we'll be left with $9,223.68. $9,223.68. So we can also represent exponential decay by changing our plus sign to a minus sign, and these ideas are still the same.